All right, guys, good afternoon. We're gonna start with the second class. As you guys are going or coming into the meeting, I'll be taking the attendance, all right? So make sure you check it at the end of the class. I'll be double checking as we are in the meeting. And in today's class, the objective is to finish chapter 1. We just have to do a couple of things. We kind of went over most of it and start working on vectors, all right? And the good thing about vectors is that it's a concept that we can revisit in chapter 3 when we start talking about two-dimensional motion, okay? Now, there are some problems in assignment 1 that require you to work with vectors, so I will be doing examples that will help you finish assignment 1, and of course, you will be able to start doing assignment 2 at the end of the class because I will start with concepts of motion as well, okay? I'm just gonna make sure that everybody is being accounted for. The class is being recorded, as you probably already got a notification, so feel free to participate or ask any questions. I should be publishing the link for the class tonight. Okay, it normally takes like an hour to be uploaded in Zoom. Once it's available, you will get a link. And normally what I recommend for long classes like this is that you skim through the recording, okay? All right, so let's review. Let's review a little bit on conversion factors. There's a question in assignment 1 about conversion factors. We went over this yesterday, right? Miles per hour to kilometers per hour. A conversion factor normally is just a number, right? Like, what is the number or fraction that will allow you to go from, say, miles per hour to kilometers per hour? Like I showed you yesterday, 1 mile is 1.609 kilometers. So the conversion factor is just 1.609. Now, a couple of you asked me yesterday about sig figs. 1.609 has 4 sig figs. And sometimes, depending on the question, right? Or depending on the grade of precision, you may actually find this conversion factor to just be like 1 mile, equivalent to 1.6 kilometers. Normally, that's what you find in some bibliography, in some textbooks, okay? This is the most precise. It has three decimal places. This one has 2 sig figs, 1 decimal place, not as precise, but when it comes to applications, if you think about it, that will give you basically the same result, right? Like, for example, 40 miles. So quickly here, right? 40 miles. If you want to convert this to kilometers, you multiply by 1.6, if I use this. And that gives me 64 kilometers. So for real life applications where, for example, on the road, right, on highways where normally you find whole numbers, they most likely just use that, okay? Now, that's simple because you only go from miles to kilometers. What if you want to go from kilometers per hour to meters per second, right? I showed you an example yesterday, but there is a way to obtain a conversion factor that you can use for different numbers, right? I believe we did 72 yesterday, 72 kilometers per hour. So let's say you want to convert kilometers per hour to meters per second. What's the conversion factor? So like we said yesterday, we multiply by 1 kilometer, 1,000 meters, and 1 hour, 3,600 seconds. And that's how I'm gonna get my conversion factor. My conversion factor is just gonna be a number, hours, or a fraction in this case. That, like I did yesterday, we cancel these two zeros, and then I have 10 over 36. That gives me meters per second, right? That to that. So that's the conversion factor or conversion fraction. Now, if I divide this by 2, I get 5 over 18. So 5 over 18 is the conversion factor that you can directly use if, for example, you are given the speed, and we're going to talk about the difference between speed and velocity today, of a body in kilometers per hour, and you want to get it in meters per second, right? That's why I used 72 yesterday, because 72 is a multiple of 18. Now let's use another number, okay? And I have the calculator here, so let's just do that. Let's say you want to convert 30 kilometers per hour. That's a good number there. Eh? 30 kilometers per hour is about 22 miles per hour, by the way. So if you want to convert 30 kilometers per hour to meters per second, right? You just use a factor. You just multiply 30 by 5 over 18. Now, let's see. This is like 150 over 18. And this divided by 3, this will be 50 over 6. Okay, now let's see. That's going to be a fraction. 50 over 6. That's 8.3. 8.3 with a period. But look, you could say it's 8.3 if you are not as strict in terms of sig figs, but we have one sig fig here. So you will run this to 8 meters per second. Okay? So that's a nice application of conversion factors. Okay? And we were also talking about sig figs. And there was a question that you see in the book and in the lab manual. I wrote it over there. And the thing is that you could find 2 different ways of doing this question. I want to show you the one that Cengage uses, all right? And that's the one that we use mostly in physics. In chemistry, sometimes they do a little bit different, okay? And it's basically how they round the final answer. Because when you have a question like that, you have intermediate values, right? 3 sig figs, 2 sig figs. If that was just the only multiplication, if you didn't have that, your final answer should have 2 sig figs. So you still have to take that into account. If you use a calculator, 4.25 times 6.7, right? I get, okay, so let's erase this. I get 28.475. Now, because 6.7 has only two sig figs, the answer you have to put in here two sig figs. And that's going to be important for the subtraction. That's the grade of precision, the level of precision, sorry. And then the other number, 2.364 times 9.82, 23. So let's do it here, 28.475 with two sig figs minus 23.21448. But the level of precision for that is 3 sig figs. So now let's just subtract 28.475, right? That minus 23.21448. So I get 5.26052. My final answer should have the lowest level of precision, two sig figs. So 5.2, but there's a 6, 5.3. All right. So we end up rounding at the end. In some, because I was taking a look at this as well in other textbooks, in some textbooks, what they do is, because these two sig figs will erase all of this, I don't know if you can see from there, like in this number, if you round it to two sig figs, you won't have any decimal place, it will just be 28. So 28 doesn't have any decimal places. So you could round the final answer like, just like 5. So it depends what rule you are using. If you use a significant figure, like we did yesterday, your final answer is like that. If you use the decimal place approximation, this will be just no decimal places. This will be one decimal place, but because this has no decimal places, the final answer will be, well, technically 5.0, right? So you just have to be careful. In physics, we use the significant rule, significant figure rule. So that will be the accepted answer, okay? All right. So now that we have discussed sig figs and units, we can start talking about the coordinate system and vectors, all right? So that is what I wanted to go over today for sure, and I'm gonna share my screen now. There. Okay. So what do you have in there? An important section on physics is the usage of vectors and the coordinate system. Now in physics 1 and even on physics 2, you are mostly going to be using the X and Y coordinate, okay? So you should know how to plot points in the coordinate system, right? You have the first quadrant where X and Y are positive. You also have the second quadrant where you have X negative, Y positive. And then you also have the third and fourth quadrant. For now, we're just focusing on this. Now, why do we need this? Because then we can build this. What you're seeing there is your famous reference line, reference angle, r comma theta, where r is the magnitude of this segment that we're eventually going to call the vector, and theta is the reference angle. It's always the angle with respect to the x-axis, like this. Okay? If the segment was on the x-axis, the angle will be 0. if the segment was on the y-axis, the angle will be 90 degrees. Okay, and if the segment was here on a negative x direction, the angle will be 180. Okay, so the idea with this r and theta is that we can quantify the coordinates using r comma theta, where again, r is the magnitude, the value, the length of this segment, and theta is the direction. Okay, so we can use right triangles there to quantify the values of x and y. You see, what we do from here to here is we build this right triangle, we draw it like this, and we call this the x and the y, that we eventually going to call the x component and the y component of a vector. And in a right triangle, you should remember the definition of sine, cosine, and tangent. Okay, and they're here, right? Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent opposite over adjacent. And in this right triangle, the Pythagorean theorem works. So x squared plus y squared equals to r squared. So this is a nice way to find the magnitude of, or the length of the segment. Okay, and in here we have our sine, cosine, and tangent in terms of y, x, and of course r. All right. So here's an example. You probably have seen this in geometry in school, where you have to find the angle. So to do that, let me just show you how you're going to use the calculator for that. As you remember, you use the sine inverse. Right? So for example, how do you get 60 degrees? You go to scientific here, and you do second sine, right? So of 0 is 0. Now let's do for this. 0.866. I go to trigonometry, the sine inverse, and that's 59.99, which we run it to 60 degrees. Okay. The same can be said with the tangent, right? If you have the value of the sine, you can get the sine inverse. If you have the tangent inverse, you can get the value of the angle. Okay, and we normally care about this because these are angles in degrees, and this provide us with a direction of a given segment, or in this case, a given vector. Okay, so let's show you on the whiteboard, right? What is a vector? All right. So you already seen the trigonometry behind what we're going to be talking about with vectors. But what is a vector? So a vector is a physical quantity that has magnitude and direction. So this is going to be important because this is how we are going to understand the difference between some quantities in physics that are vectors or scalars, right? So what's an example of a vector, right? This. A vector could be the velocity, which normally we label it like this, v and that. If you see this dash on top of a variable like this, that's telling you that's a vector. That's velocity. Acceleration. Acceleration is a vector. Like that. And then eventually, when we talk about force is also a vector because it has magnitude and direction. And there are other quantities like displacement, okay, torque, momentum. Those are quantities that have magnitude and direction. Now, what about scalars? What's a scalar in physics? It's just a quantity that only possesses a value. For example, energy, power, heat. Those are scalar quantities. There's no really direction. I mean, yes, technically, heat flows from hot bodies to cold bodies, but it's not really a vector quantity like velocity or acceleration, right? It's just energy, right? Heat is energy. And it comes from work. And work is also a scalar quantity. Now, the interesting thing about work is that we define work as the multiplication of two vectors. Okay? And that's because work depends on the amount of force. And we will talk about that. But that's the difference, right? Power, energy, heat, right? Internal energy, those are scalar quantities. So we don't care about the direction. But in this case, we do. So you can have a negative velocity, right? But not negative speed. So there you have it, right? And we're kind of going ahead a little bit. But velocity is a vector quantity because you can have a positive or negative velocity or zero velocity. When we talk about speed is the quantity, is the magnitude of the velocity, and is the, not the opposite, but it's just the value of how fast you are moving or traveling. So we only care about the magnitude in that case, not the direction. For the direction, we talk about the velocity, the acceleration, right? The displacement, not the distance. What is the difference between distance and displacement? Displacement cares about your initial and final position. Distance is just how much you travel. It can be in a loop, it can be straight, up or down, doesn't matter. You only care about how much. With displacement, you care about the direction. What is your final position with respect to your initial position? Okay, so how do we illustrate vectors? Just like this. Ray. You've seen rays in geometry. That is basically how you illustrate a vector. How do we label them though? Vector A is like that. That vector has a magnitude, which we label it like this. And it's not a coincidence. The reason we use that is because if you remember in math, that is the absolute value. And the magnitude of a vector is always positive. It's never negative. Okay? The direction can be on the negative x-axis, negative y-axis, but the magnitude, the value of the vector is always positive. That's why we use that symbol. Now, in terms of direction, right? If you see the vector like that, and we use our reference is always going to be the x and y axis like this. X and y. So if that's our coordinate system, that vector has direction first quadrant north of the x-axis. So because of that, we can use this: north, south, east, west. So the direction of the vector A is on the northeast. Okay, so for example, if that was velocity, the velocity vector is on the northeast direction, right? And how do we quantify the direction? By the angle. So we need this angle here. And for that, that's what we need our trick. Because the thing about vectors is that you can reposition them as long as you don't change the direction of the vector and the magnitude of it. I can place this vector here. So I can use the X and Y coordinate system to find the components and find the angle, the reference angle, which is the direction of the vector. Okay? Now, that's just one vector. How do we manage different vectors? Like how do we add or subtract? Because it's not like scalars. So let's see. And that's also in the book, by the way. But sometimes you can be given vectors like this. Vector A and vector B. How do you add A plus B? Or at least, how does it look? Right? Eventually, we're just going to use the coordinate system. You can put those vectors in the X and Y axis, find the components, and you can find the sum of the vectors. But you can also find this graphically, right? The way you find the sum of two vectors graphically is just by doing this. So vector A, vector B. You see, I join the tip and the tail of these two vectors. So my resultant is this. That's A plus B. All right. Graphically, that's how it looks. But there can be instances where vectors may be, so here they're making an angle. All right. How do we find vectors, or how do we add or subtract vectors in the coordinate system, like if they were here? So let's do the simple case. Right? So use this graphically. And by the way, you will need this for one of the labs. When we're doing the forces table, you have to do a sketch. And one of the sketches may look like that. Like a force like this, a force like that, and you just, so that's a sketch of how it looks graphically. Analytically though. So say you have the X and Y coordinate like this. And I give you a vector A. So let's do again the simple case. Vector A with units, say 10, the magnitude of A, and a vector like this. Okay, so to add vectors like that, we have to take into consideration the direction. To the right is always the positive X, up, positive Y. To the left, negative X, down, negative Y. So if I add the vectors, yes, the magnitude of this is 6, but this is going towards the left. This is going towards the right. So you are basically adding like this. 10 plus negative 6, that's equal to just 4, whatever units, right? So this is basically the resultant of those two vectors. It's easy if they are on the same direction, on the same axis. What happens if I place the 6 on the y-axis? Okay, let's do that exercise here. So kind of like this. That's easy. Now, so now let's place again the X and Y. But now, let's say this is the 10 and this is the 6. So now the vectors are like this. They are not in the same direction. They are actually perpendicular to each other. So how do I find the resultant of the vectors over there? You use what we call the parallelogram method. Because the angle is 90 degrees, you can build this right triangle. Where this is 10, this vector, like I said, you can move it here parallel. You are not changing the magnitude nor the direction. So this is also 6. So if this is 10 and this is 6, you can find the magnitude or resultant R. Your resultant R is none other than the Pythagorean theorem, the square root of 10 squared plus 6 squared. That's the square root of 100 plus 36, 136. That should be around 11 point something, right? 11.66 or 11.7. Now, since two ways you can actually round this, okay? You can say that's 12, but you have only one sig fixed on both of these, 1 and 1. So, yeah, I will say you can write it as 10. So, you can just, as a whole number. Whole number, that's whole number. Okay, to make sense on the result. That's to make sense because you cannot write a step, right? So there you have it. That's your resultant. All right. Now, the difference is that here it was kind of direct. Here you have to use this method because of the angle in between. All right. And there's a question in the assignment where they ask you to find the maximum sum between two vectors. So here you got 4. Here you got 12. What's another situation where you can add these vectors? The other situation is if both of them are on the same direction. So to find the maximum sum, the maximum possible value for the sum of two vectors is if both of them are parallel to each other on the same direction. So for example, if you have 10 and 6, if both of them are going up, the sum is 16. That is the maximum value of the sum. And what's the lowest? That's the lowest. The lowest is when they are in opposite directions. So that should help you for one of the questions. I think question 1 is that you have to figure that out. Okay? Or question 2. It's just about placing vectors and directions. Now, keep in mind, we're already talking about this. So now let's see how do we properly, analytically, how do we add vectors using the coordinate system and your trigonometry, okay? So you're gonna remember, recall, or relearn how to find the components of a vector using your sine and cosine, all right? So let's use another example, another value. Now, let's talk about the components of a vector. In the x and y axis, okay? Because technically you can have a vector in 3D as well, x, y, and z, but we don't have to worry about that for now. always you draw this, y, x, and let's draw a vector like that. So it's like the segment I show you, right, in the slides. Let's say this is, again, A, magnitude A, and the angle theta. So to add vectors analytically, when you have 2, 3, or more vectors, you use a coordinate system. It's easier and more effective. And additionally, for that, you need to find the components. So like this, I want to do that in here. I'm going to project. Basically, that's what you do. You're doing a projection here on the x-axis. And by doing that, I have a right triangle there where I have the AX component and the AY component. So the AX, the horizontal, is the adjacent of this angle. So my AX, what will that be? What do you think? In terms of A. Anybody?
Could you repeat that?
Huh?
I didn't hear you. Could you repeat that?
What will be the X component of this vector in terms of the magnitude A and the angle theta?
Wouldn't it be the cosine of
Yeah, it will be with cosine because AX is the adjacent, right, for this angle. So AX will just be A, I just divide that for now, A cosine theta. And my AY, what will AY be?
sine?
A sine theta. So if you're given the angle and the magnitude of the vector, you can find the components AX and AY. You can also find the angle theta if you divide AY over AX. If you divide those two, A will cancel, you get sine over cosine. That's tangent of theta. And like I show you in the slides, I can find the value of theta using tangent inverse. So my value of the angle, right, using this, is tangent inverse of AY over AX. There you are. So that's how you find the direction of a vector in the X and Y plane and the components of the vector A in this case. All right. Let's use numbers and then let's do an example. Let me just show you where you can find this in here, like what we discussed in vectors that we did. That was kind of the example with different numbers. And this is what we just did, the components of a vector. And don't forget, that's how you find the magnitude of the vector, right? Using the X and Y components. All right, and that's the angle there. All right. So let's show you an example with numbers so you can see how this works, and then let's do a few examples that you are gonna find in Cengage, so you see how this works out. The major thing about this is that you need to visualize this. Okay. So let's see. Okay. So, example. Say we have the X and Y system. Again, let's give you a vector like that, 8, and an angle of 60. Let's find the components. Right? Let's find the components of the vector. Okay. Always remember, if it's a good idea to do this, like that. And then that's how you can see this is your Y component. Yeah, let's say vector A. AY. Like that. AX. So my AX is the magnitude 8 times the cosine of the angle, which is cosine 60. And my AY is 8 sine 60. Okay. You can use a calculator and find those. However, I don't know how many of you remember, but just in case, I want to put it here, the 30-60 triangle. In that particular triangle, this is, let's use K. This is like 2K. This is like K root 3. It's a special triangle. So the cosine 60, the cosine of this angle, right, is adjacent over hypotenuse. So cosine 60 is K over 2K, that's 1 over 2. So in AX, 8 times cosine 60, 8 times 1 over 2, 8 divided by 2 is just 4. That's my X component. What about sine 60? Sine 60 is opposite over hypotenuse. So root 3 divided by 2. So this is 8 times root 3 divided by 2, 4 root 3. Okay, so now let's say we use a calculator for that. 6.9, yeah, 6.9. That's your Y component and your X component. All right. So that's how you apply your trigonometry, and that's how you find components of a vector on the plane. Are there any questions? Questions? Okay, let's do an example on Cengage, or from similar to the ones in the assignment. I found one here with an airplane. Yeah. So some examples, some real life situations. They're gonna start using the east, the west, north, south. So let's see how this works. Okay. We're gonna use the same logic, but with different angles, with different values, a more realistic scenario. Okay, let's erase this. And the following example is gonna give you an airplane going from one city to another city and then to another city. And the idea is to visualize the problem and then find the distance and also the direction relative to one of the cities. So the problem says that you have an airplane traveling to the west from city A to city B. So let's see. Let's use the X and Y coordinate because it's simple like this. And if you use that, you label it like this: north, south, east, and west. Okay? You do it like that. So from A, let's suppose A is here on the origin. It goes to B, traveling 345 kilometers. So this is A to the west here. This is B. It traveled 435 kilometers. And then from B, right, it travels 25 degrees north of west from B to C. So 25 degrees north of west, like that, like this. C. And how much? 155 kilometers. And this is 25 degrees. So that's the graph. All right, that's the situation. What is the distance between A and C? If you go a straight line, in a straight line, the distance between A and C. So basically, what is this distance? The vector as well. Well, technically, yeah, let's say the vector between A and C. What's the magnitude of the vector AC? All right. I want to show you two methods for this. Let's use the coordinates, and then let's use the cosine rule. All right, the law of cosines. All right, the law of cosines may be more like quicker. That's using geometry, but let's use what we did. All right, because technically, if I extend this, the orange, yeah, has this component and this component, this big component here, and this. And this makes 90 degrees. If I find both components, I use the Pythagorean theorem, and I find the distance, AC. So you already know this is 435. You are missing this little bit. But hey, I know the hypotenuse is 155, and I know the angle. So this is a problem of it's a problem of trigonometry. Okay, so like I said yesterday, if you have questions about the math, now is the time, because to find the horizontal and the vertical components, this will be 155 cosine, 155 sine directly. If you have the hypotenuse of a right triangle, this will be the, and you have this angle here, right? Cosine, sine, using what we did with vectors. So this little bit here, that is 155 cosine of 25. And this one here will be 155 sine of 25. Is that clear for everybody? Yep. So if I evaluate 155 cosine of 25, I get 140.5, 140. Run it. Like that. And 155 sine of 25. I get 65.5. Okay, so I have these values, right? So to find the length, I can redraw it here. I have this is 65.5. This whole leg, this is C, this is A. That will be 435 plus 140. I add these two. That will be 575. 90. So now I can find my magnitude, the length AC, which is what the problem is asking you. To find, let's call it R, that's just the square root of 65.5 square plus 575 square. Is that clear? Yeah. So those numbers, let's see. Okay, so this is square root of 336.25 plus 65.5. 4290.5. So that, if I add with the previous one, I take a square root. So 579. That's my final figure. That's how you run it based on this sig fix. 579 kilometers. That's my distance AC, straight line. So vectors is basically your trick. The second part is asking you, relative to A, what's the direction to C? So relative to the first city, what's the direction to C? Basically, they're asking you for this angle. Right? They're asking you for the angle theta in that right triangle there. You have the opposite, the adjacent, you use tangent of theta. Okay? So let's do it here. For the direction, for AC, tangent of theta is 65.5 over 575. So we find a ratio, 65.5 over 575. That gives me 0.11391. If I do the tangent inverse of that, I get 6.50 degrees. But for direction, we have to specify what's the direction. So that's 6.50 north of west, because it's the angle here. That is the angle here. So north of west. How about that? Okay. Any questions about this? You sure? Okay, now let's, so here we had a real life example with two vectors. We didn't have to add them, but now let's say that we want to add two vectors. I want to give you two vectors. You're going to have to add them, okay? One will be in the X and Y, but one will be at an angle. Okay, so let's practice that. Can I erase this? I mean, it's recorded, but maybe some of you are writing this. Okay. All right. You're going to find a resultant of two vectors. All right. One is going to be already here. 5 newtons, so it's a force. And the other one, $30 newtons, and let's give you an angle here, let's say 35 degrees. So you're gonna let's say you want to find the magnitude and direction of the resultant. This is the last example that we're doing on vectors. Then we can start going into motion, all right? And the thing is, it correlates because in motion, we're gonna keep talking about vectors because as I said, displacement, velocity, right? So how do you do this? And that's actually not bad because 5 is already, right? So you only have to worry about the blue vector, the one that is slanted. Whenever you have a vector like that at an angle of 35, right, like the blue vector, you have to find the components. Okay, that's basically the drill. You find the components and then you can add. Now, it's important that you keep in mind the direction. Now, I gave you these vectors and they are in the same orientation, sort of. Like this is on the positive x, and this vector here is on the positive x and positive y. So it's going to be simple to add the vectors, all right? So we have to find the components of the 30 Newton vector. You are gonna do this like we did before. You have the y component and the x component there. And you see, the x component of this vector is parallel to 5. So it's easy to add the x component. And the y component is advanced. So for the y component, oh yeah, so what do you guys think? Somebody? What will be the... Let's use the chat as well. Okay. So what will be the y component of this vector, of the 30 Newton?
So is it gonna be 30 sine 35?
30 sine, okay, yeah. And what will be the x component?
Oh, sorry. The x would be 5 cos 35.
Yeah. No, 30.
Oh, 30.
5 is already there. Yeah. So this is 30 sine 35. What I'm doing that, some of you calculate the value of that, okay, using the calculator. And then the x component for the blue vector is 30 cosine 35. Okay. So what are these values? What is 30 sine 35?
17.2.
For which one? Y?
For y.
For this?
24.6.
Okay. So this is by
Professor, sorry, 24.6.
Oh, 24.6.
Yep, sorry about that.
Yeah. So 17.2 is by itself. So technically, you have 17.2 just going up. And on the positive x, you have 24.6 and 5. So you add them. 29.6. And I already showed you how to add vectors that are in 90 degrees. To find the magnitude of the resultant, how will you find R? What do?
You do the Pythagorean?
Yeah. Square root of that square plus 17.2 square. Okay. I'll let you guys calculate that. And in the meantime, start working on the direction. What's the direction of that vector? Okay, so what's the magnitude of R? What do you get for R?
You guys get 33.9.
You can use a chart if you guys don't want to talk, but I mean, if I do it here,
I got 30.01 because it's supposed to be 24.6 squared instead of 29.
oh yeah, 24.6, sorry. Oh, no.
Wait, no, it's supposed to be 29 because you add in the 5.
Oh,
Yeah,
sorry, yeah, my bad.
Yeah.
But
So
yeah,
yeah, then I think the total is 33.9.
33.9. All right.
Professor, does the plus or minus matter in this or not really? Like when you take a
What?
square root? Like, when you take a square root, you have to do like plus or minus. It can be positive or negative.
Oh, no. Remember that the magnitude is always positive.
Okay.
Yeah, so no. That's for algebra. Yeah, that's when you do the roots. No, we don't. Yeah. The magnitude of a vector is always positive. Okay, so we just take the positive root and the direction.
The direction I found 34.96. It was a 10 inverse of 7. Oh, hold up. I think I added it wrong. It will be 17.2 over 29.6, right?
Yeah.
Oh, my bad. Hold up. My bad. 17.2.
30.2. Is that what you guys got? 30.2 degrees?
Yep.
Yes, 30.2. Yep.
Yeah. The way you get a direction is using, so I'm gonna do it here. For the direction, don't forget, is the theta angle tangent inverse of 17.2, the y component over the x component. That's why using components is so important. And yeah, like you guys said, 30.2 degrees. Degrees, not radians, huh? Be careful with those calculators. Make sure they're in degrees. All right, that makes sense because the result of these two will be around here. All right. Okay, so that's vectors. We're going to be doing more